Today we're going to be talking about half-life. So half-life is the amount of time it takes for half of a given sample, or the mass of the sample, of radioactive elements, otherwise known as radioisotopes, to decay into something else. Now that something else could be something that's radioactive, it could be something that's not radioactive. What is this used for? It's actually used to determine how old stuff is a lot of times, and it's found on table N in your reference table, so you can look those up. Now the reason we're able to determine time or age using radioisotopes is because the half-life never changes for a given element. In other words, here's a representation of half-life. So if these are all my radioactive atoms, I'm starting with 100% of the radioisotopes, so they're all radioactive. After one half-life, half of those will be gone and turned into something else. That's why they're not pictured. They didn't disappear, they're just no longer here because they're not the original elements. And then half won't. And then in another half-life, the half of the remaining half will decay into something else. Now here's the reason it can be used to determine time. The first half-life took the exact same amount of time as the second half-life, as the third, and as the fourth. So if you're at half-life 1 and you give that amount of time again, half of those atoms will decay into something. If you give that same amount of time, half of those atoms will decay into something. And so because half-lives they stay the same, they don't change, they're different for every element, but within the element sample, it's never going to change. You can use them like an atomic clock, and that's basically what they're used for. Now, that's a graph to show it, and now I have some visual representations that are a little different. So here's a pie chart. So if this is the original sample, let's say the half-life here was 3 days. I'm just making this up because we don't even know what element this is, but we'll just use 3 as an example. This would be at day 0. So we could say at day 0, we're at 100% of the elements. Nothing's decayed because no time has happened. So it would be the whole pie chart. It would be 100%, or it would be a fraction, 1/1. After 3 days, we would now be, so this is day 3. So after 3 days, half of those atoms would have decayed into something else. I'm using green to show that. 50%, or 1/1, to represent it as a fraction. After 3 more days, which would now be day 6, because half-lives add, but the actual length of the half-life stays the same, but we can add these up too to keep track of time. After 3 more days, half of the remaining half would now be decayed, and we'd be left with 25% that are still radioactive, or 1/4. After 3 more days, we'll call this day 9, half of that half, so 12.5%, 1/8, fraction, or you could look at it that way. Again, these may not be completely accurate. I just kind of drew these in using Microsoft Word. 3 more days, we'll call this day 12, half of that half. So now we're down to a 16th, or 6.25%. And then 3 more days, we'll call this day 15. This would be 3.125, or 132, and you can see if we keep going, we'll never hit 0. That's another important part. In this graph, you could make the argument that it would hit 0 because you're only using a small amount of atoms. But if we're using samples of atoms that are numbers that are literally uncountable, then you're theoretically never going to get to 0. And so we just say we never hit 0 when we're using larger samples of atoms. All right, and so that's basically how it works. So just be aware that half-life, the time is going to add up, but each half-life stays the same amount of time. And so we can use that fact to figure out how old things are. And we're gonna do some practice problems on the back, and I'll explain how it works. So with these practice problems, you are going to use this chart to do half-life problems. This is the easiest way to do it. I'm gonna abbreviate it HL for half-life, T for time, M for mass. Mass can be represented by a certain amount of grams of material. It could be represented by a fraction, or a percent, 100%, or 1/1 is the fraction. It could be represented by some random amount of atoms. They could call it, 39 atoms, or 3.9 million atoms. Doesn't make a difference. All right, what do we do to these columns? Well, it's pretty simple. Half-life is always going to add. Half-life is always going to add up, so we're going to count these out. So it's going to be like half-life 0, 1, 2, 3, 4, 5, and it can go on. There's no limit to how many half-lives you need. Time's always going to add up as well. If half-life is, just like on the example, if the half-life were 3 days, it would be day 3, day 6, day 9, day 12, but it's the same 3-day increment every time. That's what makes it a half-life. And then for mass, it's going to half every time. So the mass is going to go, 50, or 100, 50, 25, 12.5, or it could be, you know, it could be some random number like 39 grams, and then you have to use your calculator to half that and half it again and half it again. So you're always halving masses. So the way I like to draw these out is like this. And again, the nice thing about this is this chart, I don't draw the whole thing. Half-life, time, mass. Always start with half-life 0 and time 0, and then half-lives. You can put as many of them as you want or as you think you're going to need. Sometimes they might go out to 10. Sometimes they might only go out to 2 or 1 for that matter. All right, and the mass, notice I didn't include anything in the mass, and the reason I did that was because I haven't read the question yet, and I have no idea what they're going to use to represent the mass. But this part, every single half-life problem will start looking like this. So now we do the reading. The original sample, keywords, so the original or the starting amount was 48 grams. That's what I started with. That goes up here. So there's my 48 grams. And then they say after 6 days, only 3 grams remain unchanged. What was the half-life? So I do have enough information to solve this, because here's the issue. I know that 48 grams turned into 3 grams in 6 days, and that's all I need to know. So what I'm gonna do is I'm gonna start halving the mass, because that's what that does, until I get to 3 grams. So half of 48, 24. Half of 24, 12. Half of 12 is 6, and half of 6 is 3. So it took 4 half-lives for this to happen, and this process took 6 days. I'm just going to write D for days. Once I have that, I have everything I need to get my answer. So there's 2 ways of doing it. You could set up a fraction or a ratio. You could say, well, 4 half-lives were 6 days, so therefore 1 half-life is X amount of days. You can do that. Or you could just say, okay, if you divide the time by the number of half-lives, 6 days per 4 half-lives, I believe you get 1.5. 1.5 days per half-life. Let me fix that. And there's my answer, because they wanted to know how long was 1 half-life. Well, 1 half-life was 1.5 days. Now, if you wanted to prove that, kind of like a double check, you could go back and actually add it up. In other words, if I sub in 1.5 for the length of a half-life, that means 1 half-life is 1.5. 2 half-lives is going to be 1.5 plus 1.5, which makes it 3. And then the third half-life, I'd add another 1.5 to it, so I get 4.5. And then the fourth half-life, I add another 1.5 to it, and it equals 6, so I did it right. And there's my answer. And that's all you have to do. Let's do the rest of them, and then I'm going to give you some practice problems for this. So again, we always start with this chart. Half-life, time, mass. It's always going to go 0, 0. And again, I don't know how many I need, so I'll just put a few in. Maybe I use them all. Maybe I have to add more. I won't know until I do the problem. So a radioactive element has a half-life of 5 days. What fraction will remain after 15 days? All right, so here's what they're saying. They want to know the fraction. Well, the original fraction is always going to be 1 over 1. And now they're saying the half-life was 5 days. What remains after 15 days? Well, here's what I'm going to do. I know the length of a half-life. I'm just going to keep adding it until I hit the 15-day mark that they want me to hit. So after 1 half-life, I'm at 5 days, because they said the half-life was 5 days. So 2 half-lives would be 10 days. 3 half-lives, 15 days. That's the time they told me. So now I go over here. What fraction would be remaining? Well, I don't know. Half it until you get to that point and you have your answer. So half of 1 over 1 is 1 over 2. Half of 1 over 2 is 1 over 4. Half of 1 over 4 is 1 over 8. And that's the fraction that would be remaining. They could represent that by a percent. They could give you the fraction. It depends on the problem. It's literally just the wording. If they would have changed this one word here, fraction to percent, then it would be 100, 50, 25, 12 and a half. Doesn't really matter. Okay, but that's how you do the problem. Next one. So, half-life, time, mass, 0, 0. We'll go out to 5 this time. I don't actually know. What percent of a 1 gram sample of carbon-14 would remain unchanged after 22,860 years? All right, so that sounds like a lot of numbers, but it's really not that bad. They asked what percent. Now, they asked 1% of a 1 gram sample, but they want the percent. That's how this question reads. So if I'm going to be doing percents, I know my starting percent's always 100. I don't care about the 1 gram. All right, it really doesn't matter to this problem because they didn't ask how much of the 1 gram is remaining. They asked what percent of the 1 gram. So it's always going to be some percentage. Who cares about the 1 gram? Now, we have to look up, there's not enough information here. We are going to need to use table N for this problem because we don't know the half-life of carbon-14. So we go to table N, we go to carbon-14, it's the second one down, and it's 5,715 years, or depending if you're using, I think my reference table is old, I think the new ones maybe say 5,730 years, so whether yours says 30 or 15, it really won't make a difference. So one half-life, 5,715 years. Percentage-wise, that would be at 50%, but we're not done because we need to hit that year right there. So what I'm going to do is I'm going to keep doing half-lives, keep adding up the half-life until I hit that many years or something outrageously close to it. So after two half-lives, I'll be at 11 for 30, which would be 25% remaining. After 3 half-lives, I'll be at 17,145, which would be 12.5% remaining. The next half-life, 22,860, which would be 6.25% remaining, which is the answer. And then I didn't need the 5th half-life, it wasn't used. Now, with this problem, if you had a different reference table that said 5,730 years, you would get a number that was like, 22,000, it would be 60 higher, so 920. And I would say that's basically the same thing. That's like saying, if you're buying a car and the car is $22,860, and then they say, oh, well, there's a some tax or fee that's $60, and you may not be happy, but you're not going to say that $60 is such a large amount that you're not going to walk away. Some people might, but most people wouldn't. They'd be like, all right, fine, there's $60 when compared to the cost of something that's $22,000, or if you do it in years, if something is 22,860 years old, does it really matter if it's 60 years older? No, it's like, it's almost as old as the dinosaur. Not really, but you get the expression. And so it doesn't really matter at that distance. So if you're very close to the number that's your target number, then we're just going to round it and say, yeah, that's pretty much it. So that's how you do number 3. And the last one, number 4. After 48 days, a sample of I-131 decays to 3 grams. What was the mass of the original sample? So look what they're looking for. They're looking for the original. So we set up our chart. Half-life, time, mass, 0, 0. I usually go out to 5. I don't know if I'm going to need it, but let's find out. So now they said after 48 days, a sample of I-131 decays to 3 grams. What was the mass of the original sample? All right, let's figure out how to do this. We look up, the one thing we can look up is the half-life of I-131. So if you go to I-131, the half-life is 8.021 days. I'm just going to call it 8 days, okay? So we know the half-life is 8 days. So that means they told me after 48 days, well, if I want to hit 48 days, I'm just going to keep going. 16, so another half-life, another 8, 24, another 8, 32, another 8, 40, another 8, oh, now I got to add 1, 6, which would be 48, right? I'm going to double check my math. 8, 8, 8, 8, 8. Okay, so it takes 6 half-lives. And after those 6 half-lives, we ended up with 3 grams, and they want to know how much was the original. Well, if going forwards in half-life, right, we half it, how do you go backwards? Well, you do the opposite of halving. So instead of dividing by 2, you multiply by 2. So 6 grams, supposed to be a gram, 12 grams, 24 grams, 48 grams, 96 grams, 192 grams, I think. Let me double check that. So yeah, there's my final answer. That's the original amount, 192 grams. And so that's how you do it. So the way I set these up, that's pretty much every variation in half-life you can be given, but just remember that as long as you know that your half-lives are just going to count up normally, your time is going to add up the way time does, and your half-life is always going to half if you go in this direction, double if you go in the reverse direction, you should be able to fill out everything you need in order to get these problems done.